Hello there, this will be module 5 of DECO. Okay, in this module we'll be covering the following topics: parallel processing and pipelining, arithmetic pipelining, instruction pipelining. So these are three types of pipelines. Okay, RSIC pipelining is also there, but these are the main pipelines that we'll be discussing in our syllabus. Vector processing, array processors and multiprocessors. These three topics and pipelining is what comes under parallel processing. So we'll be starting with parallel processing first. Starting with the first topic of parallel processing. Parallel processing is basically a technique, okay, that is used to provide simultaneous data processing. That means we can execute two or more instructions at the same time. The core requirement of this to happen, where we execute two or more instructions at the same time, we need ALUs, that's multiple ALUs. We have arithmetic logic units, okay, arithmetic and logical units. So when we have many ALUs, we are able to send an instruction to each of them, so that each processor, like each unit, can parallelly process and execute the instruction. Then we have more processors as well that operate together. This also helps in executing two or more instructions at the same time. This is achieved by having multiple functional units that perform the same or different operations simultaneously. So functional units basically refers to these units we have over here. All these units are functional units. Basically each of them has a different function that it performs. An adder subtractor will add or subtract the data. We have multiplication, we have a logic and shift unit, we have an incrementer, floating point add or subtract, floating point multiply, and for floating point divide. What happens is we have registers over here that are connected to the memory, and data from the registers goes to the functional units based on the control system. Okay, and accordingly we have operations that are performed and they go back to the processor registers and they are stored in the designated registers. This is called parallel computing. So if you have multiple, for example, we need multiplication and we need shift operations, so we can send data to both of them through a common bus system, and then accordingly we can get an output. Parallel processing can be classified into three types: internal organization of processor, interconnection structure between processors, and flow of information through the system. These are basic. It's a theory by M.J. Flynn on the basic of computer instruction data. We focus on four different groups of computers. Okay, so these are computers where we have single instruction stream and single data stream. That means we have one instruction stream and we have only one data stream, SISD. For SIMD we get a single instruction stream, same as previously, but we have multiple data streams. In the third one we have multiple instruction streams but single data stream. This is only a theoretical computer system. It usually does not work this way, so we don't have any practical approach for the system. It's not usually used. Multiple instruction stream and multiple data streams, okay, that means just as the name states, we can understand the computer systems that we studied earlier. So SISD as in single instruction and single data. This is a simple computer, okay, so it has just one control unit, one processor and one memory unit. It's just a basic way of, the way instructions are executed sequentially, one by one. So a system may or may not have parallel processing. Usually it does not, because there's just a single stream of instruction and a single stream of data. When we have a multiple stream of data, this means that it has many processing units under the supervision of a common control unit. So the instructions are controlled by a single control unit, but since we have multiple data streams, that means we have multiple processor registers. Fine. Data is stored in multiple processing units and is controlled by a single control unit. In multiple instruction single data, as I said, it's only of theoretical interest since no practical system has been constructed using this organization. MIMD, where we have multiple instructions and multiple data streams, is basically a computer system of processing several programs at the same time. So a program basically has multiple instructions in it, okay, and parallelly processing multiple instructions. So this is what it refers to when we have multiple instructions and multiple data streams. So each instruction unit that controls the instruction will have its own data unit as well, data stream. So when there are multiple one of them, they can be processed at the same time using different units for each instruction. The Three main types of parallel processing that we're going to discuss are pipelining, vector, and array. First one is pipelining. Let's get started with pipelining. So pipelining is basically a technique where we break down a sequence of process into sub operations. So if you have a process, okay, basically we have an instruction set where we are supposed to do certain operations on a given data set. What we're going to do is we're going to break it to sub operations, and each operation is executed in a special segment. So there is a certain box created, a segment, okay, where that operation is executed, and then it's sent to the next segment, okay, and then again the other segment performs certain tasks on that data. Each segment performs partial processing of the task, okay, based on the way it's partitioned, and then the result from each segment is transferred to the next segment. Finally, the main result, the final result we get is when all data has been passed through all these segments. An example is for the task AI multiplied by BI plus CI, where I can be the value of A, B, and C from 1 to 7. Okay. Each sub operation is performed in a segment, so within a pipeline. So we'll have a pipeline for the whole expression, the task. Okay, and it will be broken into sub segments, into segments. First segment will multiply A and B, and we'll get the output. Along with the output, we will get the data for C, and then that will be the second segment, and the third segment is gonna add this output to this data. Okay, we'll see this in a moment. So we have the first segment where we're performing A to register 1 and BI to register 2. In the second segment we multiply R1 and R2, which have the data of AI and BI stored, and then we also input the data of C into R4. Last part, the last step of the task is to add the product of A and B to C. So R3 plus R4 gives us the final result R5. This here is a flow diagram of how our pipelining works. So we have AI, BI, and CI. Fine. In the first part, we are inserting AI into R1, BI into R2. We send it to a multiplier where they're multiplied and the output is stored in R3. Along with this output, we have a register R4 where CI is inputted. Both these values are then sent to an adder and their summation is sent into R5. After understanding how the pipelining actually works, what we're going to do is we're going to create a table where we can see how each step is carried out and how these segments are broken down. Since we said we have three segments in this pipelining, okay, the first segment is we deal with R1 and R2, which is basically A and B. Segment 2 deals with R3 and R4. R3 is the output of A into B, and R4 is the value of C. The third segment is R5, which is the final output of the task, where we add the product of AB into C with C. We have a clock pulse number. So basically these are the clock cycles. In the first clock cycle, we are inputting data of A1 into R1 and B1 into R2. Remember, we had AI and BI and CI, where I was from 1 to 7. So we are gonna execute this task all the way from 1 till 7. So what happens is, in the first one we input the values of A1 and B1 into register 1 and 2. In the second step, before we do that, we go back to segment 2 and 3. So in the first step, we do not have an output of A into B, right? So we can't store that into R3, and only when we store that into R3 can we have the input of C1, because that is an entire segment in itself. Okay, so you cannot operate half the operations of one segment without doing the other one. Just as we said, segment 1 performs its task and it sends it to segment 2, but since we haven't performed this task yet, we cannot send it to segment 2, and so we don't go to segment 3 where it is the final operation. Okay, so at the second cycle we input A2 and B2 into segment 1. So now you see, this is parallel processing. We are inputting the data into segment 1 while segment 2 performs the operation on the previously entered data. Fine. And you'll see in the third step, segment 3 is performing an operation on segment 2's previous data, and segment 2 is performing operation on segment 1's data. Fine. And segment 1 in itself is getting an input from the stored memory. So this is called parallel processing. Each of the segment is parallelly processing its tasks. Okay, so at this second cycle we have A2 and B2 inputted, fine, while segment 2 mein you can see A1 and B1 being multiplied. Okay, that was from the previous stage, along with C1 being inputted. Still no R5 because this is just the second stage, so we'll pass segment 2 data to R5 in the next cycle. As you can see, in the next cycle we go to A3 and B3. Okay, segment 2 performs the operations on the previous data of segment 1, A2 and B2 multiplied plus C2 added to R4. Okay, and segment 5 works on the previous data of segment 2, where A1 and B1 we have the product, okay, and we have C1. So these two are stored in R3, which is sent to the adder, and we get the final output in R5. Okay, same way we're gonna continue with 4. Okay, this is gonna work on 3 and this will work on 2. We'll go all the way to 7, where we have I as 7 as the last number. We're gonna do the same operations here, but what we're gonna see next is that we are done with A7 and B7. We have no more inputs for A. Okay, but since we started 2 steps later over here for the output, we're gonna end 2 steps later. Okay, this is because at 8, the clock cycle 8, we do not have any inputs for A and B, but we have an operation being performed in segment 2, which is the multiplication of A7 and B7 and the input of C7. Okay, and at segment 3 we are having the final output of A6 B6 added to C6. Here, this one goes here, fine. So the last clock cycle will be 9, where we have no inputs in segment 1, we have no inputs in segment 2 either. Okay, so segment 3 is going to perform the last data, the last operation that is there from the previous stage of segment 2. So this sums up how the actual processor, like the pipelining, works step by step based on the segments. Now this is a consideration where we will understand the time taken, okay, the number of clock cycles in a system with pipelining. So if we consider k segments, we had k as 3 in the previous pipeline, and a clock cycle time of tp, okay, to execute n number of tasks. So the first task will require k tp to complete. Okay, so why is this? Because the first task is basically segment 1, the time for segment 1 plus the time for segment 2 plus the time for segment 3. Okay, and each task takes the time tp, so we'll get k tp time to complete task 1. Then we can consider the remaining tasks n minus 1. Okay, so if each task is done per cycle, it will take n minus 1 into tp time, fine. So this will be the time, hence we can find the total time by adding the two of them. So you have k plus n minus 1 clock cycles required. Okay, basically the time taken will be clock cycles into the tasks, which gives you the total time. Okay, so the clock cycles will depend on the total number of tasks, fine, since we have one task per cycle, so that will give you the clock cycles of k plus n minus 1. The total cycles in our previous example we can calculate by taking k as 3 and n was 7, because we had I from 1 to 7, so we have n as 7. 7 minus 1 will give us 6 and k is 3, so we had total of 9 clock cycles as we saw in the table previously. Now if we see a non-pipeline unit that performs the same operation and takes equal time tn, okay, in this one we're going to take tn for a non-pipeline system. We had tp last time. Okay, what we are going to see is that the total time required is ntn, because we do not have any segments this time, so it's going to take it ntn time for performing n tasks, fine. So tn time for each task, so multiplied by n will give you the total time. Hence the speed operation is given as ntn upon k plus n minus 1 tp. How do we get this? We basically find the ratio of a non-pipeline system to a pipeline system. Okay, when we find that and turn it into s, we can say that ntn total time divided by the k plus n minus 1 tp total time of a pipeline system. From the previous equations we can see that if we consider n to become much larger than k minus 1, okay, so that means if a huge number of tasks are being performed, then when it becomes larger than k minus 1, okay, so the value of k plus n minus 1 approaches the value of n. Okay, so if we take it to approach n, under this condition the speed up becomes tn upon tp. Why is this? Because we already had ntn on the top, and if k plus n minus 1 approaches n, then both the n's can cancel out, So it gives us a simple of Tn upon Tp. Now, if we assume that the time taken for a task to be performed by a pipeline system and a non-pipeline system is the same, for example Tn and Tp are same, then we can simplify this equation to Tn equals to KTP. So for a non-pipeline task, okay, the time taken is equal to K times the time for pipeline task. Okay, so this means that S, the speed up time, is reduced to the following equation, where S equals to KTP upon TP. Fine. And thus, when simplified, because we take the times for both the pipeline and non-pipeline to be similar, we cancel them out. It becomes K. So this shows that the theoretical maximum speedup that a pipeline can provide to a system is K, where K are the number of segments in the pipeline. So this proves that the more the segments are, the faster the computer can compute the tasks and execute them. Thus, pipelining helps in parallel processing and in increasing the speed of the execution of instructions. This was it for the topic of pipelining, and we'll be continuing in the next video.